video, we are going to discuss primes, factors, and prime factorization. In particular, we have the goal of writing the prime factorization not just of numbers, but we also want to get the factorization of monomials. Now, this is a topic that I know that you've seen before, and I know that you've seen extensively. So we're going to do a quick review over the stuff that you've already done before, the things that you already know, and build upon it, adding some algebraic components to it. So first of all, informally, what is a prime number? Prime number is a number with exactly one factor. That is, you can't break it up with multiplication using any kind of a whole number. The first prime numbers you should probably have memorized: 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, so on and so forth. Composite numbers have more than one factor. And so those are numbers that you can split up. For instance, 4 can be split up as 2 times 2. 6 can be split up as 2 times 3. 10 is 2 times 5. 55 is split up as 5 times 11. Any number that you can split up into smaller chunks with multiplication is composite. Prime factorization is listing out all the numbers that multiply, all the prime numbers that will multiply to something. A factorization is just a bunch of multiplication that's the same thing. Prime factorization then is multiplying a bunch of primes that will equal the same thing. A factor tree, and this is the tool that I'm sure you've seen before, it's just a tool to get your prime factorization. Each of these things that I've mentioned so far, I expect those are reviewed. You will have done factor tree before. You've done prime factorization before. The new component that we build into is working with a monomial. We will want to create a factorization of a monomial as well. Of course, if we're going to create a factorization, we have to know what it is. We have a series of multiplication for numbers and variables. That's a monomial. For example, we could have the monomial x to the 4th power using a variable. We could combine that with a number like 2x to the 4th and have a monomial. And there's nothing special about having a positive. We could have negative numbers out in front, like negative 20. And there's nothing special about using x. It can be any variable, like m to the 3rd power. We don't know what the variable m is. We're just saying it's some unknown number. And we don't even have to stick with just one. We could actually have 2 variables. And it's okay. Each one of these pieces that I've put up there is a monomial. One part that you cannot have for monomials, though, it is not allowed to have a negative exponent. It is not allowed to have fractional or decimal exponents. You can't have negative exponents on the variables. You can't have fraction or decimal exponents. They've got to be just whole numbers that you count. 1, 2, 3, 4, 5. Those numbers are okay. These other ones are not. Now, our first skill that we want to practice is writing down a factor. Now, factors are just going to be the numbers that multiply up to give you something. For instance, what are your factors of 18? Tell me a pair of numbers that will multiply and give you 18.
9.
9 times 2 works. So 9 and 2 are factors. What else can multiply to 18? 6 times 3, absolutely. What else? And here's the common one that a lot of times students don't think about. How about 1?
1 times 18.
1 times 18 will work as well. These pieces in the blue then are the factors. Stuff that multiplies up to give you the piece, those are your factors. So we would be able to say our list of factors, and I'm putting them in order from smallest to biggest. 1, 2, 3, 6, 9, 18. Now in this particular context, we're using factors in the context of area. The beginning part of the problem told us that we had a rectangle with an area of 18 square feet. And since area is length times width, our whole numbers then have to be the length and width of the triangle, of the rectangle. Well, based on these pictures, which pair do you think this one is? Is this the 9 and 2, 6 and 3, or 1 and 18? Which one do you think it is?
What's that?
Recognize, oh, there's our 3 and 6. We should obviously recognize that really long and skinny are going to have to be 1 and 18. And then, of course, that leaves us with 2 and 9. Factors will play a role whenever you're working with area. Factors will play a role whenever you're working with rectangles. Refreshing your memory, here's a factor tree. So we will use a factor tree to get the prime factorization. First for the number 420. Now when we did that, we'd start off and say, what are two numbers that will multiply to give you 420?
42.
In this instance, we have 10 times 42. Both of those are composite numbers. And so our 10 times 42 we will break down. What are two numbers that will multiply and give you 10? 2 and 5, so we'll have 2 times 5. What are two numbers that multiply to give you 42?
7.
7 times 6. And so this one we wrote 10 is 2 times 5. 42 we wrote as 7 times 6. And now we have to continue because these numbers can be broken down further. We'll notice 2 is a prime number. That one stays by itself. You can't split up 2. 5 is a prime number. You can't split up 5. We have to leave it alone. 7 is a prime number. It stays by itself. But 6 can be split up. 2 and 3. And those are both prime, which is why we're stopping here. This bottom row, that's your prime factorization. 2 times 5 times 7 times 2 times 3. That's a prime factorization. Factorization means a bunch of numbers that are being multiplied. We have that. Prime factorization then is a bunch of prime numbers that are being multiplied. And we've got that. I would like to note there's nothing wrong with saying this piece here That is correct. A lot of times people prefer to put them in order though, so that all of the same type are put together. For instance, put the 2's together at the beginning instead of having them mixed all around. And then 3, 5, 7. Both answers are correct, but a lot of times we prefer the one in red simply because then the numbers are grouped together nicely and they're in order from smallest to largest. It helps people understand it a little bit better sometimes. Now I would like to of course note that's not the only way that we could have done a factor tree. We didn't have to start with 10 times 42. We could have started with 6 times 70. In that instance, we would split that 6 up, exactly as you told me earlier, DJ, with 2 times 3. But now we've got to split up 70. We could write 70 as 7 times 10, as you noted, Brenda, and then continue on downward. 2 cannot be split up as a prime, so we'll leave it alone. 3 is a prime, we'll leave that alone. 7 is a prime number, we'll leave it alone. But then 10 can be split up with 2 times 5. And here is a different correct one. Or rather, the numbers are written in a different order, but it's not a different answer. We only have one prime factorization, but we can write it out in different ways. You'll notice that if we take the same answer and start putting them out in order, 2, 2, 3, 5, 7. It matches exactly what we had before. Thus, we have our prime factorization of 2 times 2 times 3 times 5 times 7. And that's our prime factorization. Whether we put it in this order first, that order, or descending order, it doesn't matter which format we use, as long as the numbers are correct, the order doesn't really play a role. I will let you know that when we're working in class, this is the one I'm going to use. It's more common to put it in that way. That way everybody can understand it more easily if we go smallest to biggest. Wanted to check in. This is familiar, correct?
Yeah.
Right. I do want us to go through and have you do one on your own, checking it out to make sure that you still have the skill. And so we will come back and do some factor trees, but before we do that, we want to see how to factor a monomial. This is the new skill. This is where we're... Okay, let me put this in. Oh, I'm actually recording already. I thought I wasn't recording. I thought it was on pause. Alright, so factoring a monomial is the new skill. This is where we build upon your previous knowledge. This is where we start putting algebra with it. Now, a lot of it is going to be based exactly on the same way. We're going to start off with the 24, and with your marker boards, I'd like you to create the factor tree. Get the prime factorization for 24, and then we'll build from that. I'm going to pause the recording. And of course, there are lots of different ways to start this one. Looking at your work, the most common one I saw was 4 times 6. Splitting that up, we'd have 2 and 2, 2 times 3. And so we wrote out the prime factorization of 24 as 2 times 2 times 2 times 3. That's our first step. You will need to create factor trees. You will need to determine the prime factorization using your existing skill. The next step, though, is to start splitting up monomials. This is very straightforward. You only have to pay attention to the exponent. When we pay attention to our exponent, we'll notice that we had x to the fourth. How many x's is that?
4.
4 of them. And so we could simply write that 1, 2, 3, 4. So we still have our prime factorization, but then we'll split it up with the 4 x's. That's done. Our factorization then, 24 x to the fourth times y, when we completely and totally split it up, from the factor tree, we had 2 times 2 times 2 times 3 for the 24. Just use the factor tree to get the prime factorization of the number part. Once you've got the number part, split up the variable part. We're done. That's our factorization. Factorization of a monomial. Now continuing these. What are the factors of 28? Starting with the most obvious ones, we know that we'd have 1 times 28. 2 times 14 will work. 7 times 4 will work. That's it. We have our list of factors. What about 48?
No.
Of course, we'd have 1 times 48. 2 times 24. Does 3 work? Well, if we're not sure, you can always do a quick piece of division. 48 divided by 3 goes in once, giving us 18. 3 goes in 16 times, and because we have no remainder, 3 works. The nice part about that is it's even given us our other one. We have 3 times 16. What else? Does 4 work?
Yep. 12.
Yeah, it's 4 times 12. Does 5 work?
No.
If we took 48 and divided by 5, we'd get 9
Remainder 2.
with a remainder of 3. Because we have a remainder, but we know 5 doesn't work. One piece that students will frequently use, if you've got a multiplication chart handy, sometimes it's nice just to go across the lines of a multiplication chart. And so, for instance, we could say, does 6 work?
Yeah.
Cut across, we find 48. So yes. We can even then come straight up toward the 8 and get our other pair. There's our full list for the factors of 48. Next set that we're looking at, is it prime or composite? And what does prime mean? Prime means it has exactly 2 factors. So you can't split it up. Prime numbers cannot be split up, composite numbers can. So can 97 be split up?
Yeah.
With what?
1.
1 and 97 does not split it up into smaller numbers, though. These are 2 factors. We'll always be able to get 1 times the number itself. Is there a different way to split it up besides 1 times 97?
No.
No. Because there's no other way to split it, it's a prime number. If we had a second way to split it, that would make it composite. What about 117? Obviously, we know we've got 1 times 117, but is there any other way to split it up?
11.
Will 2 work? No, it's an odd number. 2's don't go into odd numbers. Will 3 work? could do the long division, and that's one way to check. If you remember your divisibility rules, we could also apply the divisibility rule for 3, and that would do it too. In this particular instance, we could do the long division. Get 1 there, and so we'd have 3 times 39 is another way to get it.
That's composite.
So it is a composite number. It's worth noting there are other ways that we can split that up. For instance, 9 times 13 is another one. But we're not creating a list. We just wanted to know, is it prime or is it composite? Finding 2 pairs is what tells us it's composite. Factor out these monomials. I'm going to pause the recording so that you can do both of these on your boards. When we consider our factor tree, we know 21 is equal to 3 times 7. Those are both prime numbers. So from the factor tree, we have 3 times 7. That's the number portion. Now we need the variable portion. How many of these n's should we have? 5. So 1, 2, 3, 4, 5. We're done. We have our factorization for the monomial. For problem number 6, we have to do the same thing. Do your factor tree. I'm going to take 18 as 3 times 6. 6 is 2 times 3. So the number portion, our prime factorization of 18, is 2 times 3 times 3. Now we need the variable portion. How many x's should there be?
2.
1, 2. How many y's? 1, 2, 3. And we're done. We'll have to create a factor tree to get the number part. The variable part is just nothing more than counting out for the exponent.